let's get started. Okay, so today we continue talking about collaborative design. And so David put up this diagram yesterday, and so let's talk about what this is. A collaborative design problem asks the question, given some specifications of some teams, so a chassis team could says that it could produce certain functionalities given certain resources, given the specifications of these three teams, what can the team as a whole produce? What sort of robot, which is capable of supporting a certain weight at a certain velocity can be produced given a certain amount of money? So the specification we have here for how the teams are interacting is given by this diagram. And this diagram is interesting because it's at once almost informal, it's intuitive. You can see the idea here that this line represents the idea that the motor should be supplying the speed to the chassis. But we'll see by the end of this lecture that this diagram is also formal. It provides not just a picture of what's going on, but a particular algorithm for, given each of these relationships, how do we compute what the entire capability of the team is, how this team can collaborate to design some product. Okay, so before we get there though, I want to give you a lot more definitions. I guess, well, so one more comment actually. So David said yesterday, and I'll remind you what these are, but that these things should be represented by these things he called Boolean profunctors, or Boole profunctors, which he also termed a feasibility relation. So these are precisely things, precisely sort of subsets or sort of Boolean functions and preorders that answer the question, what can be produced given what resources? Okay. So first though, monoidal categories. Let's see. I particularly want to tell you about symmetric monoidal categories. So going right back to the beginning of this course, we first introduce this notion of a preorder. So this is a set with an order relation. Okay. We also introduced the notion of a monoidal set, or just a monoid. And this is a set with a binary operation and a unit. So the binary operation has an identity element or a unit. We then saw that we could construct these things called monoidal preorders, which is set with both these structures. So the set, we call it P, and we have an order, but also on this thing we have a binary operation with unit. Then we saw the notion of the category. So this is similar, it's at once a generalization of a monoid and a preorder, but instead of putting the monoid structure, instead of being able to compose elements of the preorder using our operation, we start having ways of relationships between them, and we can compose those ways of relating these elements. So I'm going to write, we have a set of objects, a set of morphisms, and then we have this composition operation with some notion of units. Okay. So monoidal categories, so in particular you can say that preorders are a special type of category, or monoidal preorder, and monoids are a special type of monoidal preorder, and a special type of category, a category with one object. But sort of sitting down here then, we can perform this same sort of trick and define monoidal categories. So what these are categories, so that's all of that data, but they have, a monoid structure on the category. So we have a way of composing, sort of combining objects with each other and morphisms with each other in what's seen as a parallel sort of way. Okay. So the aim is to get here. But let's think a bit more about how we talked about these things, or how we represented them. We had this sort of very algebraic syntax where we could write things like p less than q. But we also talked about things like being able to write diagrams like 1 is less than 2. Over here on the world, so here in particular, if we draw these diagrams, then these things are the wires. And this is sort of how these wires can be sort of related in series. In the world of monoids, we often write sort of, this is another way to think about less than 2. We might write something like 1 plus 2 plus 3. But we might also think of this as some maybe string of processes. So you sort of start with something, you add 1, you add 2, you add 3. So in this interpretation here, these things, the elements here are the boxes, and this is series composition. And this E thing, we associate the word ether to. So it's sort of an ambient structure, but you can think of it as starting with the wire. So you always start with just nothing, the unit. Okay. For monoidal preorders, we had this sort of ordering relationship where we could put things in parallel. So I could draw things like 1 plus 2 is less than 4. I could also have another thing here that says that 3 is less than 5, and we can sort of conclude the structure lets us think about the fact that 1 plus 2 plus 3 is less than 4 plus 5. So here it's wires, boxes. Oh, maybe I meant to say boxes there. This is the parallel composition. But you can place boxes in series. For categories, we started typing this notion of composition. So, in particular, we have, say, maybe if I'm working with an object, say it starts sort of a hunk of metal and it starts as a bar of metal, then all I could do is I could do something like bend that thing, and then I get something like an open circle, sort of a crescent shape or something. Let's call it an open circle or cut circle. And then I could solder that together, and then I have a ring shape object, something like that. So the important part being here is that these processes, these relationships between things are typed. So you can't just take a bar and solder it because there's nothing to connect. So here we have, these are the wires, these are the boxes, and now they're not just, the boxes aren't just the existence of a less than sign, but an actual way of relating to things. And then this is series composition. So in a monoidal category, you've got a category, so you can do these sort of wires, boxes in series. But you've also got this thing here, a monoidal product, which gives you a notion of parallel composition. So monoidal categories, so you can see each of these structures is capturing this notion of diagram. And monoidal categories capture this sort of common generalization of all of these notions, where we're allowed boxes in parallel and in series, and they're allowed to have different types. So here are objects, and here are morphisms running between products of objects. So in all of these structures, we specify data that says sort of a monoid, this set here gives you the boxes you're allowed to use. And similarly, this set for our category gives you the wires, and this set, the set of morphism, still gives you the boxes. But we also had axioms that made sure that this data plays nicely together. So how do we think about them in terms of these pictures? Well, for example, this multiplication of a monoid is required to be associative. And what associativity means is that even though we specify a binary operation, like plus, it doesn't matter if we have a string of things, it doesn't matter which order we add them in. So these diagrams, if you compile down to this formal notation, could be ambiguous. This diagram could represent 1 plus 2, then plus 3, or it could represent 1 plus 2 plus 3. And our coherence, our axioms on the structure of a monoid say that this diagram is unambiguous. So that this is a good way of capturing this sort of visual picture. So monoidal categories, the axioms of the monoidal categories that we put between this structure are the ways of making sure that diagrams like this have an unambiguous interpretation. So with that introduction, let me give you a rough definition. So the reason this is rough is I won't tell you exactly what the coherence means. I'll just sort of lay out the structures and say that it captures this idea. So a symmetric monoidal category which I'll abbreviate SMC, because that's too long to write. And I often write these tuple. Is first a category C, and then a functor called the monoidal product from, so given any category, we can form this product category where the objects in here are pairs of objects in here, and the morphisms in the product category are pairs of morphisms in the underlying category C that go between the sort of paired domain and paired codomain. So that's a category, and I'm going to have this functor that I've called tensor that takes pairs of things, so pairs of objects, and returns an object, takes pairs of morphisms and returns a morphism. Okay. So that's the monoid structure. There's this unit I. So I also want to talk about a functor from the one object category to C. But remember, we saw the other day that a functor from the one object category to a category is just the same as an object. So that's the monoidal category. And then we have some things that help keep track of these ideas like associativity and unitality. So we've got natural transformations or natural isomorphisms. Called the, we'll say, for on X, we have this morphism called lambda X from the unit times X to X. And again, this is an isomorphism, so we call this the left uniter. We have a right uniter called rho sub X for every X. We have something that takes care of the associativity. So for every x, y, and z, we have a map from x tensor y tensor z to x tensor y tensor z. This is called the associator. And then, so right now I've defined a monoidal category, and a symmetric monoidal category says that we've got a map that sort of is a relaxed form of commutativity. it takes an object x tensor y and returns an object x y tensor x. So this is called the swap map. So these are normally called alpha for associative, and this is normally called sigma for swap. Okay, so symmetric monoidal category is this data such that these natural isomorphisms are well behaved. So I'll just write well behaved natural isomorphisms. Okay, so how does this relate to the diagrams? Well, so we interpret a diagram like that as representing the identity function, identity morphism on X, given, if I see a diagram like this, I interpret it as a morphism from X times Y to Z. If I see things in parallel,
it's series, right?
Oh, sorry, in series, this is composition. And I'll skip the types, or the objects. I see things in parallel, that denotes the tensor product of two morphisms. But what happens if I see things in series and in parallel, mixing things up like that? Well, I can, given any diagram, you can sort of trace a block along it from left to right, and then at every place where something happens, you can sort of subdivide. So something happened from here to here. So there's two things happening here. First, we can see this as F tensor H, and then we can see that it as being composed with G. So that's how you read a composite diagram like this, by sort of scanning across and dividing into vertical parts, where you sort of put a line between constant identity y's, I guess. There's some identity y's here, the identity y's here, and something happens between them. So we need to interpret that and write what's going on. Okay, so that's a bunch of material. So I'll give you a bit of a chance to digest, but here's sort of some questions. How do we interpret, that is, if I was going to use this syntax, how would I write these diagrams? Let's go F, G, H. So I'll give you 2 minutes to find a friend and talk about these things.
So would you be my friend? How is this stuff? Do you know how to take those diagrams and produce things right now? So the syntactic expression and symbols. Would you put just F semicolon? F tensor G semicolon H, yep, and 2. Indeed, yeah. But then why? What do you make of the difference between the way that one looks and the way that the body, like, it seems to have separated it out. That's the question. So you don't want it to be, right? Because visually, it's like, do I have to be that precise about? And the answer is that what's really being written in one tensor identity, composed with identity tensor G. And that is one of the well-behaved. Wait, actually, I think that's the functoriality of tensor that it doesn't matter. I need to think about that a little. Anyway, it doesn't matter. That's whichever way you put it, it's going to be. The point of this definition, or one way to interpret it, the point of all that well-behaved, always behaved and naturalized organisms is to make sure that and that is up to 2. What about 2? How are you? Like, could you interpret number 2? It means it's going, let's say that 2 outputs are called X and Y, and the input's called W. It means that C is a morphism from W to X tensor Y. So whenever you see any 2 things in parallel, X tensor Y over X and Y are in parallel.
Is that a question too?
In F, over there, he wrote X tensor Y. So whether it's boxes or wires, if they're in parallel, you put a tensor to these values. Well, you make these kind of drops.
Okay.
And in the first layer, you're going to see an identity.
Does anyone have any answers?
An identity wire.
Do you want to shout out how you might interpret this? Yes. That's one way of doing it. So this thing is F tensor G composed H. But there are other ways to do it, right? If you sort of stuck to this method of figuring out where things happen, you might divide it up into 3 parts like this. In which case you would get what? So what's this? Right, this is F tensor the identity, then composed with identity tensor G, then composed with H. And so the structure that's important here is that these 2 things these 2 expressions happen to represent the same morphism in this category. So this is what I mean by the coherence of this sort of structure here. So maybe to see this a bit more explicitly, let's jump to this thing down here. So did people come to some idea about how to represent this diagram?
Two ways.
Right, okay, so what are they?
First was X tensor Z, composed with Y tensor W.
Yep, X tensor Z composed with Y tensor W. And the other one?
And then X composed with Y.
So X composed with Y. Oh, T, that's right.
Tensor Z composed with W.
Tensor Z composed with W. Okay, great. So it turns out that these 2 morphisms are always the same. And in any symmetric monoidal category, and that's required by these axioms. In particular, it's required by the functoriality of the tensor product. So the tensor product is something that takes sort of 2, in this case, morphisms and returns 1 morphism. But functoriality says that we can either compose and then do our functor, which is tensoring, so we can compose then tensor, or we can tensor first and then compose. So that's precisely what's happened here. It's either tensor first, and then compose, or we could compose these things and then tensor them, and they're equal. So in particular up here, we can also perform this trick of tensoring and composing, or composing versus tensoring. But if we compose first and then tensor, so here is tensoring and then composing. But if we compose first then tensor, we get F composed with identity, tensor identity composed with G. And F composed with identity is just F. So it's F, and identity composed with G is just G, so it's just F tensor G. Okay. So these are both acceptable interpretations for this diagram, and they're always going to be the same in any symmetric monodal category because we have the right sort of coherence axioms on this structure. Does anyone want to shout out an answer to this one quickly?
ID tensor C compose alpha?
That's an A, but yeah, close enough.
Or wait, do you have to do the associator in between?
Oh, good question. The coherence for the associators say it's not necessary. I can expand on that afterwards.
Okay. Then tensor, or A tensor B,
Yeah.
and D.
Yeah. Great. Okay. Just so now you kind of have some idea about what this structure is, let me give you an example. So, examples. This is going to be brief, but a symmetric monodal category, that's very important because categories are enriched over this monodal category, which is in fact that has sort of been implicitly hanging around for the past few lectures, but has been hard to explicitly state. You have this monodal category. So the underlying category is set, so the objects are sets and the morphisms are functions. The monodal product is given by products of sets and also products of functions. So what's the product of two functions? If I have f from x to a and g from y to b, then I can get a map from called f times g from x times y to a times b, where it takes a pair x, y, and it maps it to a using the first, using f, and maps it to g to b using g. Right? So it's just these two maps operate separately on each coordinate. And so you might check then that, say, this thing is a monodal category because, well, it has to obey some coherence conditions, and so it might obey this last one there, C3, which people tend to call the interchange law. So, in particular, given some functions f, g, h, k of the required type, you can check that f times g composed with, say, h times k is equal to f composed with h times g composed with k. I won't write down the sort of domain and codomain of that function, but if this is sort of something that you can check, it holds true for functions, and that sort of bears out the fact that this is an example of a symmetric monodal category. Okay. Another example you can use is set and then what's called the coproduct disjoint union of sets. So some people might call this a tag union, given some sets A and B, even if they might sort of, in your set theory, share some elements in common, you kind of create a copy for each element in A and each element in B. So say the cardinality of the disjoint union of two sets is just the sum of their cardinalities. And the monodal unit for that is the empty set. So if you take a union of something with an empty set, it's the same set again. And that's sort of what the monodal unit does. Important example where this notation, I tend to be using this tensor symbol, comes from vector spaces, the category of vector spaces over some field K. So the objects are vector spaces, the morphisms are linear maps, and the monodal product, the monodal structure, comes from what's known as the tensor product of linear maps and vector spaces. And then fourth, important example, which we're going to discuss for the rest of this lecture, is the category of profunctors. So here, our objects are the V categories for some, let's just say, symmetric monoidal preorder V. Our morphisms are V profunctors, which I'll remind you of the definition of in a second. And then our monoidal product is product of preorders, sorry, of V categories. And there's an associated notion of product of profunctor that goes with that. And I guess there's a sort of one object V category, terminal V category, which forms the monoidal unit. Okay. One quick remark before I expand on that. So what's going on in this diagram is known as the process of categorification. So what we see is here, say we have this structure of a preorder, is we have that things can be related. And when we categorify the notion of a preorder to a category, we replace this idea, this sort of whether things are related or not, with a set of ways that they're related. And similarly, that's the process from a monoidal preorder to a monoidal category. And in fact, just as a monoid is a one-object category, a monoidal category is a one-object two-category. The example of a two-category you already know is the two-category of categories, where we not only have objects which are categories and morphisms which are functors, but morphisms between morphisms, which are natural transformations. And so this sort of picture continues. And it's sort of an important way to think about enriching your structure. Well, enriching is probably abused here because we have the notion of an enriched category. But sort of adding detail, adding more color to your structure to describe richer and richer phenomena. One thing to notice, though, is that as you go up and talk about sort of more relationships between the way things relate to each other, you weaken your notion of coherence. So sort of equality happens to usually be a notion of coherence that occurs right at the top. So there's no way to talk about maps between elements of a monoid, so we just say they're equal for the associativity condition. Whereas here, we have a bit more structure because these things are objects, and we have a way of talking about the way objects are related, which is the notion of a morphism. So instead of saying that x tensor y tensor z, x tensor y tensor z is equal to x tensor y tensor z, we ask for an isomorphism between them. And then further on, ask that the isomorphism be coherent in a natural way. Someone asked during that last section, I said natural here and talked about these natural things being natural isomorphisms, but the notion of naturality we introduced is the notion of natural transformation, which runs between functors. And the functors in here are kind of invisible. But what the functors are, say in this, let's say in this third case, which is perhaps the easiest place to see it, there's these two things, x tensor y tensor z and x tensor y tensor z, represent functors from c times c times c to c. Right? So the first functor says that you've got three things, you tensor the first two, and then tensor that with the third, and you get an object here, or a morphism here. And the second functor says that you, well, do the other thing. And so this notion of natural isomorphism is a natural isomorphism between these two functors.
So that's alpha there?
That's alpha, yeah. And being an isomorphism means there's a natural transformation in the other direction called alpha inverse, such that it's an inverse when you compose them in both directions, they give the identity. Okay. So that's symmetric monoidal categories. Let's move slightly closer to the topic at hand, which is this resource theory idea, or collaborative design idea. So let's go to, yesterday David worked sort of generally with respect to some symmetric monoidal preorder. But I just want to talk about things in terms of Boolean categories, which are Bool categories, which are preorders, just because it's easier. So there's a nice fact, or something that we're exploring at the moment, is there is a symmetric monoidal category, Profunctors. So maybe Profunctors, let's figure out what the structure is in Boolean Profunctors. So this is a category, it's a symmetric monoidal category. So the objects we saw are preorders, are Bool categories. The morphisms are these things called feasibility relations. Or Bool Profunctors. So for example, there are a bunch of ways to think about these. What is a Bool profunctor we talk about phi from P to Q is a map, is a monotone map that is a Bool functor from P times Q to Bool. That is true for us. So, for example, we might have, say, a set of all cakes, or a set of all sets of, we might have the set of all cakes and take the power set of that, and we might have some set of costs, and we might ask.
So the T's there are different T's?
Oh, this is the power set. I guess we should make it scripted or something. What cakes? And how many cakes, or in particular, which cake can I buy for the resources, the dollars that I'm going to hand over? So a very simple example, let's assume there are only 2 cakes in the world for some reason. And so they're going to be chocolate cake and favorite cake flavor? Favorite cake, anyone?
Strawberry.
Strawberry, okay. We're going strawberry. Okay, so there's a pre-order. Okay, so let's assume that cakes, instead of cakes, let's just use chocolate and strawberry. Strawberry. Then a profunctor from here to here might be, in terms of this, we have all our options. We have nothing. We have a chocolate cake, a strawberry cake. We have chocolate and strawberry. Then we have the amount of money we can hand over. We can hand over 0, 10, or 20. And the relationship sort of asks, like, can I buy 0 cakes for no dollars? Yes. Can I buy it for $10? Yes. If you give me $20, I can also give you no cakes. If you give me $0, I'm not going to give you a chocolate cake. If you give me 10, I will, and if you give me 20, I also will. Same goes true for strawberry cakes. The cakes seem to be costing $10. And if you want both cakes, you have to give me $20. Okay, so that's one way of thinking about a profunctor. Another way, which David talked about, is the collage, which says that you sort of draw these cosets here: chocolate, strawberry, chocolate and strawberry. Have a coset here. And then you have these sort of bridges that say you get 0 cakes for $0. The minimum for them is $10, and to buy both you have $20. And so you can ask, if I have $20, what can I get? Well, you can get anything. You can get that from anything. If I have $10, you can get a chocolate cake and a strawberry cake, because there's a path from that to 10. And from $0, you can get nothing. There's only a path from nothing. Okay, so the for profunctors. How does this form a category? We can compose these. So composition is given by this formula that is essentially matrix multiplication. So these are, you can think of as matrices. So given some profunctors, the composite profunctor here, so it tells you, you give it a PR pair, and it tells you whether you can get it, and whether you can get it is determined by doing an OR over OR Q of phi of P Q and psi of QR. So this should remind you of this formula that says the multiplication of matrices is sort of sum over A, B times sum over B. Okay, so here's another profunctor which says, given some money, how much category theory can I give you for some money? So I can give you no category theory, or I can give you 18 SO97. And if you give me no money, I'll give you no category theory. But apparently, if you give me any money, I will give you some category theory.
Wait.
So
for 20, I can't get any category theory?
Oh, whoops, that's the, yeah, no. Okay, that's a better diagram. Okay, so the matrix for this is what? 0, 10, 20.
Oh wait,
No category theory.
it's the other way around, right? This is how much money you can get for category theory.
Yes, it's how much money I can get for category.
Oh, so you're getting paid 20.
Yeah, I'm getting paid 20.
Okay.
7. Then we have this truth table. This is the matrix that corresponds to figuring out what the paths in there say. Okay, so question, how many cakes can I get for teaching category theory? Question, cakes for CT, question mark. So why don't you, with a different friend, look at firstly how you might compose these two matrices using this formula, and secondly check that that might agree with what happens when you can put these diagrams side by side and trace out paths. Yep.
In this diagram right now, wait, we might be reading this wrong, but isn't it possible to get from 0 to category?
Oh yeah.
Well, that's because it's possible to be paid. It's possible to have $0 after category theory because you have 20 after category, so you can have 0. Because this is how much you're being paid, and you're allowed to throw away what you're paid.
Yes.
Don't you have a problem with the fact that your monies are opposite on one side and then not opposite on the other? So you have to sort of keep track of that.
No.
Yeah.
You might think so, but that's a similar question to the one that was asked of David yesterday about why these things don't have to be their domain, even though it says up here it doesn't have to be an opposite poset. And that's this idea that somehow going down in this poset is asking for less, which is the sort of right direction, and you're interested in paths. It's not obvious, but it takes a bit of thought and then it's obvious.
So we're supposed to multiply these matrices?
Yeah. So maybe I'll speed up and just we can multiply it together.
Intuitively, the answer should be like you get the And I guess that is the relevant solid matrix will be like a true to true column, right? Without that, I don't see it anymore. That probably the bottom column, like the bottom row. So that means if there's any true on the bottom row, so true and false, or true and false, or true and true. It's also possible to get this well, okay, let's verify that. So it's true. Oh, well, because it's true.
Okay. So what's going on here? If I want to multiply these two matrices, right, it becomes, this matrix has 4 columns and 4 rows and 3 columns. This matrix has 3 columns and 2 rows, so I end up with a 2 by 4 matrix. And so how do I compute, say, the entry here? Does anyone? It's true? So it's true because if we do true and true, or well, it doesn't matter. As soon as you have true and true, it's true. But it's true and true, or false, and that's true. So similarly, because this row is all true, in fact, this column is going to be all true. But here we see true or false is false, true or false, and true or false are all false. So it's false or true and false is false. True and false is always false. So this entry here just ends up being the OR of a bunch of falses, which is still false. So we end up, similarly going down, we end up with this matrix here. And so what are the entries here representing? These are the cakes, and these are the category theories, or the amounts of category theory. And so you see that from, if I provide 0 category theory, I get, wait, what cakes can I have for dollars? What cakes can I have for category theory? Okay, if I provide 0 category theory, I can get 0 cakes. But if I provide any category theory, I can get any cake I want, and all the cakes I want, every single cake, which is what's happening in this diagram, right?
You might want an arrow.
Any category theory, there's an arrow, a path from any option here, where if there's no category theory. Sorry?
And you need an arrow there.
You need an arrow.
A green arrow. A green arrow on the right. All the way on the right.
All the way
On the right. Yeah, right there.
Ah, yes, I do. Thank you. Okay, that's composition of profunctors in a nutshell. That's the category structure. I promised there was a monoidal category structure, so that's that. The monoid structure is given by the product. I guess that's what this thing says here. So given P, so the objects P and Q, I get that sort of goes to the tensor product is P times Q as a poset, and given two profunctors, which are maps from P times Q op, P op times Q to true false, what I can do is I can put the two profunctors. So if I have a profunctor from P op times Q, P to Q and a profunctor from R to S, then I can combine these two together by taking and to get a profunctor from P times R to Q times S. Okay. So lastly, I want to talk about, go back to this diagram. So far I've told you how to run through this thing and compose these things sort of here and here, so I can take the product of this with the identity profunctors and I can compose those identity profunctors. But I have these sort of weird loops here in my sort of intuition for what is going on. So how does this ambient structure of a bull category capture these loops? And so there's another, even more structured form of category known as a compact flows category. So here's a definition. In a symmetric monoidal category, we say that X and X star are dual objects, so they're objects. And now they're going to be dual objects if there exist morphisms, so it's a symmetric monoidal category, let's call it C tensor I. Then we want morphisms from I to X dual tensor X, and we're going to call this the unit, and so eta, so we have a morphism from X tensor X dual to I, I'm going to call epsilon, such that in string diagrams, so this thing has the eta can be written as the morphism from the monoidal unit to X dual tensor X, and we can perform this composition with epsilon. And so now we have a map from X dual to X dual, and I want this to be the identity on X dual. And similarly, we can compose them in the other direction. So we have eta going there, epsilon eta. So this ends up being a map from X to X, and I can ask that this is the identity on X. So X and X dual are, X and X star are dual objects if there are two morphisms, eta and epsilon, that obey these two equations, which are written in string diagrams. So the prototype you should have in mind here, if you're familiar with this example, is a vector space, and it's, well, a finite dimensional vector space and it's dual, which is where the name comes from. Okay. So what is a compact closed category? A compact closed category is a category where every object has duals. Definition. A compact closed category is an object, is a category, a symmetric monoidal category, where every object has a dual. So for example, there's the category of finite dimensional vector spaces in terms of R. But there's also the category of profunctors. And this is the example that's relevant to us. So you might ask, in this category of Boolean profunctors, what are the duals? So here, sort of V dual is the dual vector space. Sounds awfully tautological. Here, if we have some pre-order P, then we take P star to be equal to the opposite pre-order is dual. But then, if I say P op is the dual, you're going to ask me for a profunctor from 1 to P times P op, and also a profunctor from P op, times P to 1. Okay, these are eta and epsilon. So what are these profunctors? Well, a profunctor from P times P op to from 1 to P times P op is the same thing as a functor from 1 op, which is just 1 times P op to the Boolean values, true, false. And there's a functor from here to here, which we've used many times, called less than. So given a pair x and y, sorry, these ops are the wrong way around. Given a pair, let's call them p and q actually. If you take a pair p and q, then you return true if p is less than q and false if it's not. Similarly, a profunctor from p times p op to 1 is the same as a functor from p times p op times 1 to true false, and we can also use this less than, the same order. So you might notice that these profunctors look very much like the identity. That is the identity profunctor, which David quickly mentioned yesterday, and that sort of is the flavor of what's going on in the compact closed category. So in particular, in a compact closed category, you have these snake equations, or zigzag equations, and we sort of briefly mentioned at some point that when a structure is sort of ambient to the structure of the category, we often use a special icon for them to make it seem sort of more part of the structure and not just a hypothesis, a bit of data that you're adding in. So in this case, we just draw sort of eta as a cup, or something like that, and epsilon, something that looks like that. And this explains how we're working in this diagram here. So this cup here represents this unit, or co-unit profunctor there. And so now, since this properly just represents a profunctor, you can do your things where this is a profunctor, you tensor it with, or you times it with this thing, you compose, and you go across, and you can compute the feasibility relation represented here just by matrix multiplication, which is the point of this unit.
Would you put a box around epsilon, just for me?
Ah, sure. Okay.
Well,
So this cap here might more formally be represented like this. This thing might be represented by these profunctors that look like this. Great. Please stick around if you have any questions or you just want to talk.